let the problem is 1000 water drops, each with a terminal velocity v, are combined to form a big water drop. What will be its terminal velocity is? That's the question that's being asked. So what is happening here is there are so many water drops, small water droplets, 1000 that is. They're all each having a terminal velocity v that is given. They're all now merged, combined to form a big water drop. What will be its new terminal velocity? That's the question that's being asked. So, to solve this, first of all, we shall know the formula of the terminal velocity. What is the terminal velocity formula as we have derived earlier? Terminal velocity is 2 by 9 r square, that's the radius of the drop, density of the body minus density of the fluid, that's of the medium, into g by eta, coefficient of viscosity. So if you observe carefully, 2 by 9 is constant, density of the body, density of the fluid, acceleration due to gravity, coefficient of viscosity, they're all constants. So when you eliminate all of them, what you get is terminal velocity is directly proportional to square of the radius. What are that radius are not given for you? Let's assume the small drop is having a radius r, big drop is having radius capital R. Let the number of the drops is n. We will make it 1000 later. So I have to get the answer, get the equation in terms of number of drops. So what we can write, terminal velocity 1 by terminal velocity 2, that is terminal velocity of small drop is r, terminal velocity of big drop is capital R whole square. But the problem is I don't know either small n or capital N. I have to eliminate both of them and finally write this in terms of number of terms itself. For that, what we can say, as it is given, small drops are combined to form a big drop. What we can say is the volume of big drop is sum of volume of n small drops. Isn't it? Because the mass is conserved, density is constant, volumes has to be the same. You add all the small drops together, big drop will come. Volumes cannot disappear. So taking that into consideration, volume of the big drop is 4 by 3 pi capital R cube, assuming like R is the radius of the big drop. Volume of one small drop is 4 by 3 pi small r cube, but there are n number of the drops like that. So what can be got cancelled? 4 by 3 pi, 4 by 3 pi can be cancelled. So what will be remaining? If you write the equation, what will be remaining? Capital R cube is equal to n into small r cube. If you take cube root on both the sides, capital R is n power 1 by 3 of small r. Thus I got a relation that I want between this small r and capital R. Let me just substitute this relation, this nice relation we have got. What happens then? Here, V1 by V2 is, let's leave small r as small r. In terms of capital R, let me write this value. That is n power 1 by 3, that is number of the drops power of 1 by 3 into small r whole square. Then small r and small r can be cancelled, that is 1 by n power 2 by 3. That implies velocity of the big drop is number of the drops power of 2 by 3 into velocity of the small drop. Velocity of the small drop is given as v itself. Number of the small drops that is given for you is 1000 in the problem. So 1000 power of 2 by 3 into v. 1000 can be written like 10 cube power of 2 by 3 into v. This cube and cube will cancel. That is 10 square v. That is 100 v. So if the small drop is having a velocity v, the big drop will have a velocity of 100 times of that v. That's how we need to solve this problem. To solve this problem, to reiterate, we are using a concept of terminal velocity. Terminal velocity is the constant velocity acquired by a solid body when it is passing through a viscous medium. And that is directly proportional to the square of the radius is the key concept of this problem. That's it. Thank you for watching.